Matt in the streets.
Greetings and welcome, friends. Today we're starting a brand new zone. Welcome, boys and girls of all ages, mathematicians, everybody. Today we're talking about exploring polynomial functions. That's right. And today's section heading is specifically polynomial functions. Seems somewhat redundant, but we're going to explore it like it's some awesome purple-blue forest. Oh, it'll be wonderful. So first of all, I wanted to talk about a polynomial of one variable. Notice that, let's see, a sub 0, a sub 1, a sub n minus 2, a sub n minus 1, a sub n. There are n many terms here, and I've got x to the n and x to the n minus 1, and then x squared and x to the first, and no x, because there's x to the 0 sort of thing. This is essentially what we refer to as a polynomial of a single variable. It would be like this, 3x squared minus 2x plus 1. This is a polynomial of a single variable, whereas like 3x squared y is not of a single variable because I have
two variables.
Yeah, two variables there. So that's what I mean by a single variable. Also, the thing I want to point out is that there are no negative exponents. So 3x to the negative 1, or the same as 1 over x. That is no longer a polynomial in our classification.
It's illegal.
Sure, although we would call that a rational function, and we'll talk about those later on in chapter 9. So the first thing I want to point out is what polynomials of one variable are, and here we also have polynomial functions of a single variable, just so you can understand what I mean by that. It's the same sort of idea. So let's say I wanted to evaluate, let's do a little example, just to get some practice with polynomials and stuff. So here's my polynomial, and let's say I wanted to evaluate the following. Let's say I want to know what is f of 0.
So should we label A, B, C, D? A, B, C?
Oh, like part A?
No.
Oh, no. I see what you're saying, though. You were going to imply, like, the idea of, yeah, right, the coefficients.
Yeah.
If this was an x squared, then, yeah, we could call that A, B, and C. But that's not what we're doing right now. I just want to figure out what is f of 0. So that would mean go through, plug in 0 everywhere you see an x. And let's see. 0 cubed is 0. Negative 5 times 0 is 0, and I think you see this quickly boils down to just being 1. So that means that f of 0, all right, or the value of my function when I input 0 was 1. If I want to think about this as an ordered pair, you could think about having written this as 0, comma 1. That's the same sort of information, just presented in a slightly different format. All right, so there's f of 0. We'll call that like part A of the example. Let's try a part B here. Let's calculate what would f of negative 2 have been. So what does f of negative 2 mean? It just means I'm going to go through, plug in negative 2 everywhere I saw an x.
Which would give you negative 4 times 3 is...
Nope, that does not say that anywhere here. Remember, we have to PEMDAS this, so the exponent occurs prior to the multiplication, so don't you ever multiply.
It's really going to be 2 times negative 6? What?
Negative 2 cubed means negative 2 times negative 2 times negative 2. So yeah, so that's going to be negative 8. Negative 5 times negative 2 is positive 10, and then plus a 1. So 2 times negative 8 is negative 16, plus 10 plus 1. So that's negative 6 plus 1, or negative 5 overall. So f of negative 2, right, is negative 5. Or like I said, you could always write that as an ordered pair. Just so you're aware that those mean the same thing. Mean the same thing. And not only can I plug in numbers into a polynomial function, I can plug in letters or variables, things that represent, actually this isn't, see, this is actually going to be another example because it's a different function. It's a different function. Bam. So let's evaluate. So if g of x is the following, 3x squared minus 8x plus 3, let's calculate what is g of a plus 2.
So what are we writing?
This. So here's my function that I gave us, and now this is what we're evaluating. I want to know what is g of a plus 2. So I'm actually plugging in not just a variable, but an entire expression,
Oh,
a
are we
plus
doing
2.
what I want to do, like get the coefficient and say, like, so A is 3?
No, this is a different a than the a that you're thinking of.
Sorry.
You're thinking about the quadratic stuff. Still, we're just, this a is just some unknown value to us. Some variable. So if I calculate g of a plus 2, that means everywhere I saw an x, I replaced it with an a plus 2. And of course, you guys know how to expand a plus 2 all squared. I'm just going to write that as a squared plus 4a plus 4. If you foiled that by itself. We also could distribute. And yeah, so just so you're aware, the pattern that I used there was, right, the a plus b all squared equals a squared plus 2ab plus b squared. So that's where this expansion came from. Distribute the negative 8, so negative 8a minus 16, and then plus 3 still hanging out at the caboose. And then whoop, whoop, whoop. So I've got 3a squared plus 12a plus 12 from further distributing, minus 8a minus 16 plus 3. And now I can simplify this. I've got some like terms, the 12a and the negative 8a. Those guys are buddies.
And you can circle the 12, the negative 16, and 3.
Sure. So combining everything, I'll have 3a squared. Let's see, 12a minus 8a is
Plus 4a.
4a, and 12 minus 16 is negative 4. Negative 4 plus 3,
7. Nope.
negative 1. So this would be the same as g of a plus 2. So this is what I got when I actually plugged an expression into a polynomial. So yeah, so that's less common, but it can happen. Something to be aware of. Something for us to know about.
That's scary.
Are we ever going to have one that's like G of 1/3?
Sure, they could be like that.
Why?
Because things exist. Let's talk about graphs of polynomial functions. I want to do some comparison between all of them and then draw some conclusions based off of that. Functions. So this is going to end up being a bunch of these. You guys will just end up drawing like kind of rough little sketches of these things. So the first thing I want to talk about is a constant function. And a constant function is when there's no variable represented at all. Yes, indeed. So, for instance, if I had y equals 2, or in this case, f of x equals 2, you would end up just having a horizontal line, right? Because the slope is 0. Roots, I indicate that there are 0 roots, right, or x-intercepts, because notice it's parallel to the x-axis. Or it's possible I could have infinitely many roots with a constant function if it was f of x equals 0, because then it would have just like been intersecting with the entire x-axis forever. So that is a possibility there with the constant function. The next type of function, 1 degree higher, is when, okay, let's get a variable in the picture. That'd be a linear function. So here's a sample linear function for us. And I'll show us a graph of what that looks like. And as far as the graph, just like draw a quick little squiggle or line or whatever these look like. because we're talking about these very generally. So here, notice both of these do represent lines, but what I want to point out about the constant function is that the lines can only ever be horizontal. They always have a slope of 0. These linear functions are actually a little bit more interesting. And then regarding the number of roots, there's one root that you'd have occurring, right? Notice it would cross the x-axis somewhere. And the number of bends, I'm finally coming this into play. Notice this is a straight line. There's no swerves or anything like that, right? So that's what I would call 0 bends involved there. All right, and that concept will make more sense as we continue our exploration. All right, so let's look at some more. Next, we'll look at the quadratic function. So instead of x to the first, we've got an x squared. And you guys are masters of quadratics. You know how to put them in vertex form. You know how to put them in standard form. You know how to solve them a variety of ways. And a quadratic is a parabola.
Oh boy.
And notice my possibilities for roots. I said 0, 1, or 2. Now in this case I have 1 and 2 roots for my little swoop. And like I said, just draw like a quick little swoop. It's the general shape of these things that we're talking about today. So the roots are 0, 1, or 2. I could have 0 roots if it never crosses the x-axis. So if it opens up and is above it, or if it opens down and is below it, that would be 0 roots. And it is possible to have 1 root if it's like a little ricochet, like just barely came by and kissed it on the cheek and then ran away because it was embarrassed. Right, so it is possible to have 1 root as well in the case of a quadratic. But the maximum number is 2. And then the other thing I want to point out is the number of bends. What do I refer to as bends? A turning point. All right, notice it changed direction, right? It was decreasing, 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 stops, and then changes direction. So that's what I mean by bends with these polynomials. And we'll have more specific names for them later on. But don't you fret, don't you fret. Now, you guys have not yet seen the graph of a cubic function, but they do exist. And these are all increasing in complexity. In terms of the equation, we're getting 1 degree higher in every one of these cases, right? And the graphs are becoming slightly more interesting as well. Now you might think like this is almost like 2 parabolas that like are holding hands.
But it's not.
But yeah, these curves are actually different than parabolas. They're not symmetric. So for instance, if this is where they're holding hands, this half of this part is not mirrored with this half of that part. Okay, so those are actually, even using the word half is probably incorrect. So I just want to point that out, that these curves, I mean, in general, yeah, you could kind of think of them as like a couple of parabolas. But in reality, they are not quite that same type of curve. And these actually get much steeper than parabolas much faster as well because of the cube coming into play. Now the number of roots is 1, 2, or 3. So notice this particular one has 1, 2, and 3 x-intercepts. It could have 2 x-intercepts if it was like this and just like a little ricochet, right? That would have been 2. Or it could have had 1 where it's like this, where it's just 1. But notice it cannot have 0. 0 is an impossibility for a number of roots.
Because it would always expand this way.
Yeah, it goes this way for it. Yeah. I mean, and I can even have like my little squiggle down underneath, but it's still eventually going to hit the x-axis.
You could have them this way though, right?
That technically still would have an x-intercept, but it would also no longer be a function. We'll talk about those later. That would be something of like x equals y cubed rather than y equals x cubed.
Oh, okay.
So yeah, it is possible to have something like that. But even if it was like this would actually still cross somewhere further down. And then what do I mean by number of bends, 0 or 2? Here's 2 bends. But it is actually also possible to have a graph that I might say is 0 bends, where it just like does something like this. This could technically still be a cubic function, where this isn't really a bend in the way that I'm saying bend here. It didn't change direction. Notice it was going uphill, uphill, uphill. It was less steep for a minute there, but then it started getting more steep. It never started going downhill. All right, that's what I'm referring to as bend in this
Would it
case.
ever have one bend?
No, it can't have one bend, because if it has one bend, yeah, it would I can't get it to go back up. Because one of the interesting things we'll talk about later is end behavior, and it turns out that the end behavior for a cubic is always in the opposite directions. All right, it comes in one way and goes out another. Where a parabola comes in one door and then runs out the same door. Right, it came onto the stage and then left the stage in the same direction. So yeah, it's actually impossible to have one bend. So that's a good point to point out. So let's take consideration of quartic functions.
Are you kidding?
So quartic functions, something of this form. Here I've got a whole bunch of terms to it there, and these are pretty great. Yeah, we're gonna look at least one more, I think. But you can catch it later in the video if you want, since you're leaving. But just quietly leave when you're ready then. So here's a quartic function, and these I like because it gives me an awesome W for Watty. How cool is that, right? W single U O T I. Oh yeah, bam. That's all right. I am one of the only Brian. I'm probably actually the only Brian Watty on the planet. It's such a unique name. I'm your grandpa? This is insane. So, one of the things I want to point out here, roots. Notice 1, 2, 3, 4 roots, as many as 4. I also then could have any combination all the way down to 0. Now, why could I have 0 in this case? Because it's possible that I could have my W all above the x-axis and then never come back. Or I could have an upside down W, more commonly referred to as an M, and that never crosses the x-axis as well. So yeah, so that is a possibility to get 0. Notice I couldn't get 0 roots on a cubic though, because it has to go out one door or come in one door and go out the other. So it has to end up crossing the x-axis in order for that to happen. So for quartics, you can have as many as 0 roots. And then the number of bends, it's 1 or 3. So notice what I mean by bends here. Here's 1, and here's 1. So there's a total of 3 bends there. And then you can have a quartic with kind of one bend where maybe it's got this little dimple, and then it's got a bend there. Something like this would be a quartic. So this is a true bend, and then this is just a dimple, or whatever you want to call that. So that is possible, but I would refer to that as one bend in that case. So hopefully you're starting to see a pattern forming between the degree, the roots, and the number of bends. But let's just solidify that concept with one last example of this type anyway. Let's look at quintics. Quintic function. And quintics have even squigglier graphs. And the number of roots for a quintic is as many as 5, right? So I think you can imagine if I had like this, you could have 1, 2, 3, 4, and 5, as many as 5. but not less than 1. The same reason with the cubic from earlier. It comes in one door and goes out the other. So like in this case, you can see there's only one root. And then I can actually have any number between. It's possible to have ricochets. You could have all sorts of crazy stuff with these. So quintics. So the number of roots is as many as 5, and the number of bends is as many as 4. So here's my bends: 1, 2, 3, and 4. Right? So let's consider some facts that maybe you've gathered about these. What could you tell me about the relationship? Well, what could you tell me about the relationship between the number of roots it has and the degree?
The maximum number of roots is the same as the degree.
Right? 5 and 5, 4 and 4, 3 and 3, 2 and 2, and then even over here, right? Technically, the degree here is 1, 1 and 1, and then this is x to the 0, and it's possible, right, to have 0 roots. This is actually a really abstract case right there, so I don't necessarily consider that as interesting per se. So it turns out that the maximum number of roots is the same as the degree. All right. So let's write that down. Maximum number of roots is the same as the degree. I don't know why I didn't have that one as one of my pre-given notes. Ba-ba-bam. Let's see. So, and I'm going to actually have a handful of other facts here for us. Or, yeah, as the degree of the polynomial function. So here's some facts for us to consider. Right, so the maximum number of roots is the same as the degree. Other fact about roots: even degree polynomials, it's possible to have no roots, right? Because they can exist all on the same side of the x-axis, right, above or below it. And notice, what do I mean by even degree? Even, notice, as in like 4th degree, can have no roots. 2nd degree can have no roots, right? A 6th degree could actually have no roots as well. An odd degree polynomial must have at least one root. Okay, and you saw that the 5th degree, the 3rd degree, the line has at least one point that it crosses the x-axis on. The maximum number of bends is one less than the degree. So notice that the relationship here, the number of bends, 5th degree polynomial had as many as 4. 4th degree polynomial had as many as 3. Right? So that fact seems to be verified right there. And then let's talk about end behavior. And what I mean by end behavior is where it came in and where it left, sort of thing. Like what's going on at the extreme values of it. And it turns out that even degree polynomials have end behavior in the same direction. Right? So like, for instance, this w came in from the positive side, goes out the positive side, sort of thing. And similarly, what do you think we could say about odd degree polynomials? Perfect. Perfect. So all sorts of wonderful little facts for us to consider. So odd degree polynomials. Oh, had this little chunk right here. It's like it grew there. Bam, look at that. I see a little jog right there. So odd degree polynomials have end behavior in opposite directions. Correct, correct. And to verify that, I just want to show you this picture. You don't have to draw this. Ooh, sneezes. Why, thank you, friend. So here we are. So here's some example of some even degree polynomials. The green one's a parabola, so that's x squared. The orange one, I believe, is x cubed, or sorry, x to the 4th. The purple one is actually an x to the 6th. And notice that all of them come in from the positive side and all of them go out the positive side. All right, so that seems to make sense. And the way you would describe this end behavior, this notation you should write down because this is actually understanding what this means is important. This is how we describe end behavior. So what I'm saying is the function f of x, or this is the same as the y value, y approaches positive infinity as x approaches negative infinity. So that's describing this side here. So it's basically saying as x goes to the left, y was going up. All right, is what that says. And then the second fact, what? Yeah. Yeah, you could draw a little sideways 8. This is how I draw them. And mine are never perfect. And then let's see, the second fact says your y value, or f of x, approaches or goes up as your x value goes right. And so notice over on this side, notice y was going up as x was going right. So this is math speak to describe that end behavior. So as x goes to the left, y is going up. As x goes to the right, y is going up in this case. All right. Or like we said here, it could be the same direction. If these were upside down even degree polynomials, just like how we've had upside down parabolas, it's possible that both of these could be negative because you can't actually have like a, right, that's like an 8th degree polynomial or whatever. Wow, that almost looks like a cool like ghost with like his hands raised up here and he's like, ooh, how great is that? I love it. And he's got like horns for some reason. Maybe he's like a bat ghost. I like it. So that's even degree polynomials and their end behavior. And then odd degree polynomials, as we said a moment ago, have end behavior in the opposite directions. And in a moment, we're going to actually do Simon Says for odd degree polynomials. It'll be oh so much fun. And even degree polynomials. So odd degree polynomials, so the green line is x to the first, the orange line is an x cubed, the purple line is an x to the fifth. Those are all odd degree. And notice, what do we see? That their end behavior is matching in similarity, right? They come in from one side and they go out the other for all of them. All right, so notice that my y values are in opposite directions. So y goes down as x goes to the left is what this first statement says. Or I could say, or and maybe is better, y goes up as x goes to the right. So all of these, right, they're going this way. So y is going up as x goes to the right. And over here, these are all going this direction. So y goes down as x goes to the left. So that's what I mean by end behavior. What is the extreme most values for all of these? So let's do an example with end behavior, and then we'll call it a video. So describe the end behavior of f of x equals x squared plus 2x minus 7. So to analyze the end behavior, I look at two things. I look at the degree of the polynomial. So notice that this is a 2 here. So this is actually an even degree. And what does that tell me? That tells me same direction, right? And then the other thing I look at is the leading coefficient. Man, I'm getting some lag. And that tells me whether it's what direction it opens, or, yeah, in this case, because it's even degree, I could say open. So whether I flip it or not. Okay, so in this case, I have an even degree, and it's a positive leading coefficient, so just like a parabola, I'd expect it to be kind of this shape, right? And even if this was an x to the 8th, maybe it has some more bends in here, but the end behavior is still matching. And if this was a negative number out in front, then it would just be an upside down parabola, right? Or an upside down right, crazy shape, but the end behavior is determined based off of the degree and the leading coefficient. Okay? And where that's a little bit tricky is we're all good with parabolas. So actually all of the even polynomials are easy because you could think of all of these as opening up here. But the odd degree polynomials are a little bit weirder because, right, they come in from the negative side normally and they go out the positive side for the y value. So you just kind of have to know what an upside down odd degree ends up looking like later. But that's fine. So how would I write this? Well, I would say that f of x approaches. Let's see, let's describe this side. Where is y going, up or down? Up. So approaches positive infinity as x approaches, and over here, where's x going? X is going to the left, so we describe that as negative infinity. All right, so that described this side. Essentially, that's math speak for it goes up as it goes to the left, right? And now let's describe this side. F of x approaches, it's going up, so that's positive infinity. As x is going to the right, that's positive infinity. Right, and notice that even degree, same direction, the y values are going in the same direction. They're both positive in this case. And if it was upside down, because of the leading coefficient, then both of these just would have been negative.
How come the last one is that positive or negative?
Oh, this one's positive. Sorry, I didn't specify. Good call, good call. So thanks for watching, Internet friends. Have a great day. Bye-bye.